Right guys, I'm going to do a quick video here, just continuing on from where we left off there the last day. So we looked at a pH equal to minus lambda to the base 10 to the H% concentration. I'll give you a number of questions there at the week in relation to that. If anybody had any major difficulty with any parts of those questions, will they get on to me, let me know, so I can create a little video just highlighting them. I think I'd gone through most examples, so I think if you follow the examples you should have been okay with them. A big thing I probably mentioned the last day around these is that these are all for what we call strong acids and strong bases. So for the next kind of 2 or 3 pages in the textbook, I start talking about strong acids and strong base and what they actually are. We did a whole chapter on acid base before. We looked at the idea of the Bronsted-Lowry acid or base, and basically that a strong acid is one that dissociates almost completely to produce H plus ions, or a strong base would be one that would dissociate completely to produce OH minus ions. It's got to do with the percentage of the dissociation as opposed to how strong it is. So don't get mixed up between concentrated and dilute solutions and strong and weak acids. You can have hydrochloric acid in a dilute solution, it will still be classified as a strong acid because it will still dissociate to produce almost 100% dissociation of H plus ions. Okay. Now the reason we're talking about that is because as we go through this and we look at the acid base we're going to deal with in the future, we're going to see that there are a number of acid bases that aren't strong acids or strong bases, so they dissociate to different amounts, and as a result of that then you're going to get differing amounts of H plus ions and OH minus ions produced. Okay. So I'll get into that in a second. Just I suppose a few little things on this. We know the pH of acidic solution is less than 7, neutral is 7, and greater than 7 is a basic solution. So that's just kind of stuff from before. We've looked before, we did titrations at indicators which would change colour depending on whether they are acids or bases, and we have a whole kind of little section on indicators at the back end of this chapter which we'll chat about as well. There's just a list of different substances that are acidic or basic, and then we're getting into this whole idea of the dissociation of acids and bases in relation to whether they're strong acids or weak acids. Okay, so what signifies whether you have a lot of dissociation or a small amount of dissociation is relating to the dissociation constant. Okay, now the dissociation constant is basically like the Kc we would have seen before. Okay, and basically Kc is just a ratio of your products to your reactants. Okay, so here if we look at this guy here, so there's like an acid producing H plus ions and A minus ions. So basically the HA is breaking up to produce H plus ions and A minus ions. Now what's important here is the more that this breaks up to produce your products, then the more of these that will be present. Okay, if there's more of them present in the top line here when you write your Kc, or Ka in this case, when you write it, that number will be bigger than the denominator, and if the numerator is bigger than the denominator, then that will make this a bigger value. So the bigger the value for Ka, the more it signifies dissociation. The smaller the value for Ka, the less it signifies the value for dissociation, or the amount of dissociation that occurs. Okay, so what we're going to do now is when we calculate pH, is we're actually going to bring in this idea of incorporating the dissociation constant, because if you just take every acid as strong and weak, you're just going to get random values for pHs, but some acid bases don't dissociate completely. So you see here like hydrochloric acid has a high Ka, and then as you move down here, nitric acid high, like ethanoic acid, which is a weak acid, we see there's 1.8 by 10 to the minus 5. So the dissociation is tapering off there depending on the different types of acids that you're dealing with, methanoic acid there as well. So you're seeing that as you change the different types of acids, whether they're strong or weak, their dissociations will change as well. So they're all relative. So every acid will be different as regards to dissociation. Okay. Again, then this stuff that you'll see on these 2 pages again is all about the acid base. So I'm not going to go through it here because we've looked at it before. You can have a quick read over it. It should all make sense to you as regards to the whole idea of strong acids, weak acids, conjugate acid base pairs, and so on. And there's actually a little question there at the bottom of page 287, just kind of, I suppose, bringing all that stuff together. What I really want to get into here today then is looking at the calculations in relation to strong acids and then obviously weak acids. Here's 2 examples that are in the textbook there. I think they're on page 288, and look at they're the same as before, right? The ones that we've done there before the weekend. Calculate the pH of 0.4 molar sulfuric acid solution. Okay, Now, when we bring in the fact that this is a dibasic, sorry, just put this back to work. That this is a dibasic substance, it means that when it dissociates to produce H2SO4 produces eventually two H pluses. Okay, so for every one molecule of H2SO4, you're actually ending up with two molecules of H plus, which means if you have a concentration of 0.4 H2SO4, you will actually get twice the concentration of 2H plus. So when you're doing the concentration of this to put into your minus log to the base 10, the formula we've seen last week, you're literally going to be putting in 0.8 as your concentration. Does that make sense? Oh, I can't hear you. So, yeah, so you're going to be putting in your 0.8 here for your minus log to the base 10, and you're getting 0.097. Okay, so just watch for that. If it's HCl, it's fine because HCl is going to dissociate to produce one H plus ion. So the concentration of the acid will be the same as the concentration of the H plus ions. If you have a dibasic or a tribasic acid, if you have phosphoric acid here for some reason, your actual 0.4 would be multiplied by 3 because that would actually produce its H3PO4. So it produces 3 H plus ions. Over here then, the pH of 5 grams of sulfuric acid in 250 centimeters cubed of solution. So really what we're trying to do is find out, again, it's sulfuric acid, which is H2SO4, right? The key thing here is that's going to produce 2 H plus ions, right? Now, your big job here actually initially is to get out what is the concentration of the sulfuric acid in the first instance. So again, you're saying that if you have 5 grams in 250, you'd have 20 grams in 1,000. And then you do a number of moles as mass by the molecular mass, taking 20 here divided by 98, so it's 0.2. So it's 0.2 moles is the concentration of this sulfuric acid, but it's producing 2 H plus ions, so therefore it's going to be 0.4 moles, okay? And that's what you put into your minus log to the base 10, okay? So have a look at those. Then pH of weak acids and weak bases. Now, I think at the top of page 289 to go, or maybe 291, let's double check. No, not that one. Apologies now. Oh yeah, sorry. One last thing on this. The previous guys. The pH of NaOH was a base. NaOH produces one OH minus ion. So therefore the concentration here is 0.15. You bang that into your formula minus log to the base 10. You get 0.15 and 0.15 and you get 0.82 as your pH. Remember though, this is a base. So what you're doing is you're taking your pOH. So what you're actually going to do is take the 0.82 from 14 to give you 13.18 because it's a base. Okay, the second question here is pretty similar. You can have a look at that as well. This guy then, in relation to calculating a weak acid. So they go through this whole calculation here on the bottom of page 290, the top of page 291. I wouldn't look into it too much. What's important is these two formulas here. So basically what's going to happen is they're going to tell you to calculate the pH of something. Now if they give you a question where they ask you to calculate the pH of a substance and they mention nothing about dissociation values or Ka or Kb, all you're going to do is take your concentration, say if it's HCl, take the concentration, put it into your minus log to the base 10 formula and you're done. Okay, what you have to do in these guys then is where they tell you that you have a solution of ethanoic acid, and we know ethanoic acid is a weak acid, but they tell us here, look at the Ka is 1.8 by 10 to the minus 5, right? So what we have to do is use this formula here, so we can get the H plus ion concentration by literally going and saying, okay, it is H plus is the square root of Ka times the molarity of the acid. So that's going to be the square root of, so Ka here is 1.8 by 10 to the minus 5. And then multiply that by the concentration, which is 0.1. Okay, so that's going to give us, hang on 1 second. Sorry, square root 1.3416 by 10 to the minus 3. Now that's the H plus ion concentration, okay? But what you then need to do to get pH is you take your H plus ion concentration and you're going to bang it into your formula, okay? So what this formula does is it gives you a way of calculating the H plus ion concentration and then you're taking that. So it's not as easy as just saying, you can't just take 0.1 and bang it into that formula because you're not getting the complete disassociation here. So what the formula here does, first of all, it allows you to calculate your H percent concentration. In this case, you've got pH equals minus log to the base 10 of 1.3416 by 10 to the minus 3. So very quickly, minus log of 1.3416 by 10 to the minus 3, and we get 2.87. So the pH is 2.87 in this case. Okay, and they're all done the same. There's no difference. The only difference would be you would get a base, and if you got a base, what you'd have to do is just be careful that at the very end you subtract your pH. Also watch here, at this one give ethanoic acid, so ethanoic acid dissociates to produce 1 H plus ion. If the substance disassociates to produce 2 H plus ions, like sulfuric acid, or like phosphoric acid dissociates to produce 3 H plus ions, you would take this value here and you multiply it by 2 or 3 if it produced 2 H plus ions or 3 H plus ions. Okay, so just be careful of that before you sub it into your pH equals minus log to the base 10 concentration. Right? So guys, there are the calculations I want you to be working on over the next kind of couple of days, well, today and tomorrow. So here are the questions. They are at the back end of the chapter. I want you to work through them. They're all based on these guys here, right? So they're pH, so weak acid and weak bases, because they all have dissociation constants associated with them. Okay, so I want you to work from 18.6 down to 18.10. Same method as before, just take a photograph of the questions that are done and put them into submit them through Schoology. Please let me know if you have any issues with the questions that we had for to submit from Friday. If there are any problems with any particular type of calculation, let me know. I'll put a quick little video together just doing a couple of the questions for you. Just be specific on the ones that you want done. Okay guys, take care. Hope you're all well. Bye bye.